keep an eye out for more people joining the class. Let's do the slideshow. Let's see. Let me find where we left off last time. Oh, we didn't get the, we couldn't get the PowerPoints to come up last time, could we? Do you remember? Yes. Okay. But what I'm trying, yeah. Well, wait a minute. Somehow, I think what happened, I got my, here it is. Okay. No, we're still on this first slide. Okay. Um, we'll be getting to that next slide in just a moment. So let's get our slideshow set up from current slide. We'll be ready to roll. Now, Molly, can you speak yet? I see your microphone's there. Molly Morris? Hello. Well, now our microphone went off. Okay. Molly's new to the class today, and I just wanted to go over quickly with her if she can hear me, but I don't want to say it if she can't hear me. So Molly, is there any way you can let me know whether you can hear me or not? Can you turn your microphone back on? All right. Only one I can see is Macy, and I don't see your microphone on either, but that's okay. Yeah, now your microphone's on, right? Molly doesn't even show a microphone yet. No, there it is. Molly, well, it went back off. So Molly, can you hear me? Okay. Do something to your screen. Act like even if you can't say anything, say something anyway, even though I can't hear you, and then you'll probably bump up on the queue. So Molly, do something. Can you hear me? Okay. I guess we'll have to go and get started. I can't remember where we were when we left off last time. I know where we were in the book, but we went through the syllabus. We went through everything on Blackboard, okay? And let me just show Molly this. Hopefully she can see it. And this means I'm going to have to go out of the screen again. Let me not do it yet. But Molly, are you familiar with Blackboard? Is there some way you can signal yes or no? I don't know. Okay. I'm going to assume you know how to use Blackboard. And when you get into, well, you must because you got into the class. That's where it was located. When you go to content in Blackboard, and here maybe somebody else coming in. Let's see. I don't see anybody else, but something. She did. Okay. I thought that might be it, but this screen is blocking it, so I can't see that. Okay, great. Thank you. I saw it just for a moment, and then this thing got in the way, so I couldn't get to it in time. Okay. So on Blackboard, you'll see the syllabus is there. Please read the syllabus. And if nothing else, if you have any questions about the syllabus, please either email me, message me in Blackboard, or wait until next class and ask those questions. Okay, that's there. Once you're satisfied that you understand everything in the syllabus, then you can sign that last page or type your name on the last page, email it to me, message it to me on Blackboard, or yeah, those would be the two ways to do that. Okay, just that last page to indicate that you've read it and understand it. Okay, so that's there. This won't be necessarily the right order. I think my locator card is there showing me you when I'm in class, when I'm out of class, when I'm on campus, which is at home, off campus, not supposed to be working any longer, though I'm still at home. Also show my email address. That's also on the syllabus. those kinds of things. And I wanted to point something out to you. Some of the blocks of time when I'm not in class are called advising, and that's when you can get in touch with me. I'm sorry, office hours. You can get in touch with me any of those office hours. I'll be up here. Now, I may be doing something else and may not notice I get an email, but you can contact me during those office hours. Now, if it says office/advising, that means I'm required to be doing advising at that time too, but people sign up for it. For instance, I had 2 hours of advising this afternoon, not a single person signed up. Wednesday, tomorrow morning, I think I've got one 30-minute advising in the 2 hours I've got there. And Thursday afternoon, I think I've got one 30-minute advising in the 1 hour that I have there. So I won't be advising the whole time, but it may be if you can't get in touch with me in those times that say office/advising, it may be I'm advising someone then. I'll get to you as soon as I finish with that advising. Okay. Next on there would be the research paper. No, this class doesn't have a research paper. Sorry about that. My other classes do. Okay, let's see. I don't see anyone else coming in the class. Did she send me another message? This box is blocking it, so I can't see. But anyway, let me just move this a little out of the way. Okay, I'll try it there for a while. Okay. Next after that, and in various order, the PowerPoints are out there. When I first put them out there, I'm not sure. I know my computer wasn't reading them. I don't know why. It's a new computer, first week that I've had this computer. My old computer did them fine, but I did some adjusting to them. Hopefully what I've got out there is stuff you can do. What I had earlier, I put them as documents, and I found out they work better if I put them as uploads. So I put them as uploads, so maybe that'll make them easier to open. Has anyone tried to open the PowerPoints? No, okay. They're very pathetic, so they're really not worth it. But if you do try, they're out there. Hopefully you can open them. Okay. I think that's most of what's, the big thing. All right. I see two more messages. Okay. I guess this is chat. It says, is anyone else having a hard time hearing? My something is breaking up every word. And someone else says, yes. Okay. She's got, yes, she's familiar with Blackboard. Are any of the rest of you having trouble hearing me? Okay. It is raining where we are, and sometimes that does mess with our Wi-Fi signal. Okay. It shouldn't, but it does. So if that's the case, if it's raining where you are, Molly, it may be that that's messing up with yours. The other thing, now generally I talk really loudly. Am I too loud for anybody? Or you can adjust your volume. Okay, so you seem to be okay. So it could be, I know that when I talk with the dean, I can hardly understand anything she says. I think there's something wrong with her microphone. But anyway, it sounds like the other people are hearing it okay, or at least Macy is, because that's the only one I saw her shake her head. I can't see the other people. So anyway, so I'll close this out for a moment. I only have the one mic that's in the computer, so that's the only thing I can go from. Okay, now I was just going to say, one of those topics in Blackboard says PHY112 YouTube videos. Okay, and when you go to the YouTube video file and click on that, you'll see just a whole string of videos. The ones at the top are the oldest ones. The ones at the bottom are the newest ones. The one at the very bottom right now says PHY112 syllabus. That's when we went through the syllabus. We went through the whole works last week. So Molly, if you can go to that YouTube video, you will see and hear just about everything that we did as a class. Okay? and then I'm recording this one for this time. Now, what I'm going to do, the last time I taught the course, I had a computer with a writable screen. It was a tablet computer. It had an ionizing pen. I could write and work the problems on the screen. That computer died. In fact, it died twice in the spring, late spring, and I couldn't resurrect it the second time. I got it up after the first time by getting a new adapter, a new um, battery, but after that, it wouldn't come back. It worked 4 more days after that and then died again, and I could not get it back up after that. So I do not have the capability of writing on the screen anymore. Okay, what that leaves me with, I'll be writing on a piece of paper and holding it up in front of the camera and letting you see what I've written. Now, the trouble with that, well, number one, it's probably hard to read. This is just something from last time. Okay, it's probably hard to read, but the other thing is it's probably not being recorded. Did anyone look at last Thursday's YouTube video? Did anybody? I don't remember if we even did a problem on there. I don't think we did. So um, you wouldn't have had opportunity to see that. Um, so we'll see. If you can see what I hold up in front of the screen, if that shows up on the recording, that may be okay. But I'm going to leave the last times I taught this course, I'm going to leave those videos up as well as this term. That way you can hear any new stuff I'm saying this time, but you can see all the problems worked from last time. So I'm going to leave them both up there. The ones at the top are the oldest one. The ones at the bottom are the newer ones. Okay. I took off the one that was the syllabus last time just because things have changed a little bit. All right, if there's no other questions, I'm going to get started with only 4 students. We are up to something like 10 or 11, 12, something like that, and yet only have 4 here today. So I hope the others will be coming in. We had just been talking about, and if you have your text, it's on page 124. I don't know if any of you have e-text. I don't know if you have page numbers, but we're right at the beginning of chapter 5, forces. 5.1 is force and the law of inertia, and that's what we're getting ready to talk about, the law of inertia, which is Newton's first law. Now, someone give me some indication. Do any of you have books? I don't think last time you did. E-book or regular book? Yay or nay? But one person has an ebook, but everybody else is just ordered. Is that right? Oh, I see. Okay. So it'd probably be beneficial for me to, yeah, type out stuff. Okay. Let's see if I can do that now. I'm going to do a new share here, and this time I'm going to do the whiteboard. Okay. And this is going to be pathetic, folks. Okay. Let's see. Ashton Oliver. Oh, is he in the class? Let me see. If he has, he's just added. His name's not on here now. I don't know. It must have been something else. It was something about chemistry. Okay. Now, Newton has 3 laws of motion. The first of these is also called the law of inertia. It's either Newton's first law or the law of inertia. And here's what it is. My typing is pathetic, and since you don't have, not everybody has text, a book, I'm going to type it in here. Okay. It's the law. Can everybody see this screen? That I'm typing law of inertia. Okay, you can. The law of inertia is also Newton's first law. Okay. And here's how it's stated. A body that is in motion, if I could type, my fingers do not qualify here, with the same velocity. And what we mean by that is at constant speed and in a straight line. Oops. Okay. And a body at rest continues at rest unless an unbalanced force, and that's also called an outside force, acts on it. Said a pun it in the book. I'm shortening it to own it. And outside usually has an E in it. Okay, sorry about that. My typing is bad and I'm not used to this keyboard. It's a new computer. Okay, new for me anyway. I think I'm going to lengthen this out just a tad. Okay. The law of inertia, also called Newton's first law, a body that is in motion with the same velocity at a constant speed in a straight line, or a body at rest continues at rest, or the body in motion continues in that motion, unless acted on by some sort of unbalanced or outside force. Okay. Now, here's basically a dumb example of it, but it certainly works. Okay, let's say you're playing softball or baseball. The pitcher throws that ball pretty hard, however they throw it. You swing at the ball. If you miss the ball continues at same direction, same velocity, pretty much, and not as bothered by your missed swing. Okay? Because that ball, that object, that body was not acted on by an outside force, an unbalanced force. Okay? However, if you do hit the ball, then the ball changes its velocity. Now, you might hit it into the ground for a foul ball or a ground ball. You may hit it up in the air for a fly ball. Doesn't matter. You've changed the direction of that ball. You've changed its velocity and you've changed its, well, velocity means both direction and speed. Now, Molly, we talked about this last time, or at least in my memory we did. Velocity is a vector quantity. Speed is a scalar quantity. Scalar just means it only has a magnitude. 75 miles per hour, 190 miles, whatever, 15 feet per second, 3 meters per second. That's a speed. But if that velocity has a direction to it, a velocity will always have a speed associated with it, but also a direction. So that ball coming in at a given direction, at a given speed. If you hit the ball, you're the outside force. You change its outside force. You change its velocity, which is its speed or direction, usually both. Now, let's say you're golfing. The ball is sitting there on the tee. It's at rest. Now, sometimes those pro golfers take practice swings and not hit the ball. The ball sits there because it's at rest. It's not been acted on by an unbalanced force. However, once that golfer hits the ball, it's changed its velocity. That means it's changed its speed and changed its direction because it had neither when it was at rest. So that's what the law of inertia is. A body is going to continue in its state of motion, whether it's moving or at rest, and if it's moving, constant speed, straight line motion, unless it's acted on by an unbalanced force. Okay, let's give another example. I usually give this one in class, so you'll have to visualize this. What if I were to roll a bowling ball down the center aisle of the classroom, if you can imagine that? Okay, if none of you sticks your foot out and kicks at that ball, you're pretty smart because that probably would hurt. So the ball continues that straight line motion until it hits the wall in the back and makes a big noise, and they fuss at me for messing up the baseboard. Okay? But if some of you did stick your foot out and kick at the ball, you're probably going to make it go off in a different direction. You are then the outside force. The ball is going to continue at a constant speed, straight line motion, unless acted on by an unbalanced force. Okay? That's Newton's first law of motion. Okay? Now, why it's called inertia, we're going to get to that in just a moment. So let's get to it right now. Okay? So what is inertia? This is on that same page. And here's what inertia is the property of a body that, I lost my place here, causes it to remain at rest if it is at rest. Yeah, goodness gracious. That's awful, isn't it? Was someone trying to tell me this? Goodness gracious, what is that? Okay, first, the S should not be there. Okay, the rest of it is garbage. Okay. My fingers got off the keys, didn't they? Pretty badly. The right hand was completely out of place. Terribly out of place. Oh boy, to remain at rest. That's supposed to be if it is that's supposed to be at, I think. Okay, I believe that's it. If it is at rest, or to continue moving with a constant velocity unless an unbalanced force acts on it. Okay, they like to put upon it. I'm going to shorten it. That's what inertia is. The property of a body that causes it to remain at rest if it is at rest, or to continue moving with a constant velocity unless an unbalanced force without an extra E in there acts on it. Okay. Now, that sounds a lot like the law of inertia because this is the definition of inertia. Now, inertia is most closely related to the quantity of mass. How much of that object is there? Okay. Now, we're down to 3 students. I guess we lost Molly. Okay. Maybe she's trying to fix her sound. But the rest of you can still hear me okay? Yes? Okay, I hope so. Okay, let's picture rolling the bowling ball down the center aisle. We've already said if you kick your foot out there to move it, you're probably going to hurt your foot. Why? Because that bowling ball has a lot of inertia, okay? It has a lot of inertia because it has a lot of mass. Now, if I were to roll a ping pong ball down the center aisle of the classroom, y'all probably stick your foot out there and no problem and divert that. Why? Because ping pong ball has very, very, very little mass. In fact, it has so little mass that even wind is going to move the ping pong ball, not going to have much effect on the bowling ball. So therefore, inertia is related to the mass of an object, the property of a body that causes it to maintain its state of motion. And that's why this is called the law of inertia. All right. Now let's see if we can go back to a different share here. That's the PowerPoint. Oh, there it is. Why it shows up twice, I don't know. Can y'all see that okay? Okay. Need to go from current slide. Okay. Now, this guy is straining like crazy trying to push this box, whatever this happens to be, over a driveway, it looks like. He's not wearing his mask, but this was before. Never mind. Okay. He is pushing on the box. There is a friction force between the driveway and the box, and that's resisting his motion. He's pushing with a force in that, and to the left, let's see, can you see my cursor? You see the arrow that's moving on the screen? Can y'all see that? Okay. The guy is pushing with a force in this direction. See how much he's straining? The friction is pushing with a force in this direction. Those forces are exactly the same, but opposite directions. Forces are vector. The net force acting on it is zero, so he's not moving it. He is not moving it. Now, if he were to submit a little bit greater force here, and this were to stay the same down here, then the net force acting on the box would move it. But as long as these two forces are balancing each other out, neither one of them are an unbalanced force, you have zero acceleration. Therefore, Newton's first law is in play. Okay? Probably not the greatest example, but a decent example of that. Okay? Now, that's several. I told you the PowerPoints in this book are pathetic. That slide there goes several pages on. We're now on 124. That's on page 140. So there will be no new slides for that long. Okay, so we're stuck with the guy pushing the box for now. That's an example of Newton's first law. If there's no unbalanced force acting on it, his push here is being balanced by the friction force there, so therefore there's no net force acting on the body, on the box. Okay. Same thing goes for a car. They show this figure in the text. I'll hold it up so you can kind of see what I'm talking about. Okay, can you see the pictures of the red car there? Am I holding the book in about the right place? Okay, now the top car apparently is moving because friction's acting on it. Okay, it's also got air resistance opposing it. There's friction between the car and the road, and there's friction between the air and the car. Okay, now does air have any friction to it? Have you ever? Now, I remember doing this when I was a young kid. It made my dad pretty angry when I did it. But I loved to stick my hand out the window because we didn't have air conditioning. This time of year, you usually had the windows open. Now, if it's raining, we had to have them closed. But when it wasn't raining, the windows were open because you die in that car with suffocation. So anyway, and we did most of the traveling in the summertime to go see the grandparents and stuff. So anyway, when we were driving along, I like to stick my hand out the window and feel the wind. If he was going 60 miles an hour, boy, that would almost take my arm off, throw my shoulder out of joint. But if it's going slowly, I could put it out there. So if at the higher speeds, there's more air resistance. At lower speeds, there's less air resistance. Okay. So this car must be moving because it's hitting air resistance and friction in the road. Now, if the forward thrust of the car exactly equals those resistances, then it's going to be traveling at a constant speed. If it's going at a constant speed, there's no net force acting on the car if it's at constant speed. However, if you step on the gas and you speed it up, now you've overcome the friction. Now there's a net force moving it forward. Now, most of the time, frictional forces won't push it backwards unless it's a very, very strong wind, but we're going to pretend there's not. Okay. Now, the second car down here, can you see that one? Looks like it's on ice. You can't now? Okay, you see it? That car, I don't know, hopefully you've never tried to drive on ice, but it doesn't matter what you do, which way you steer your car, which way you push on the gas or the brakes, the car just keeps going in whatever direction it was. That's because ice has no friction, or very little friction, and therefore nothing is changing the direction of the car. Inertia is taking hold, and the car just goes wherever it was going, it continues going in a straight line. You turn the wheel, it keeps going the same way it was. You step on the brake, it keeps going the same way it was. You hit the accelerator, the wheels just spin on the ice, it keeps going the same way it was. Okay? That's an example of no friction, no air resistance, and therefore the car continues a straight line motion no matter which way the wheels would turn. Now, the top of the next page is an example of what they call an inertia trick. Has anyone ever seen anything like that? Can you see that? It's a penny on a glass on a cardboard thing at the top of a glass, right? You see that? Okay, I've done it with a uh, a mass on a piece of paper on a tabletop. You can do it a variety of ways. If you have a tablecloth that doesn't have very much of a seam in it, just a very slick tablecloth, you can do with this with dishes. Don't do it with Mama's fine china, though. Okay, in case you mess it up, you don't want to break anything. But what you do there is give a very quick jerk, either on that piece of paper or whatever you're pulling on, and generally the object stays right where it was. Okay. Um, I'm going to try it this way. I don't think it'll work, but I'm going to try. Can you see me holding the book here? Okay. I'm going to put this pen on top of the piece of paper there, right? You see the pen on the paper? Okay. I'm going to do a real quick jerk of the paper. See, the pen hardly moved. Why? Because its inertia kept it right where it was. There wasn't enough friction between the paper and the pen to make it move very far. It moved maybe a little bit, but maybe that was because I pulled on it weirdly. That's an example of inertia. Okay? Pulling a tablecloth out from under the plates. If you do it right, the plates stay in place. If you don't, you may have a crash. Okay? Do it with silverware. Don't do it with glasses and plates. Okay? See if you can get it. Now, let's go back to our whiteboard. Okay, and let's do another, oops, my text box is left. Text box, okay. The text box is not coming up. Why isn't it? I've got the drawer here, and you don't want me trying to write with the keypad. Okay, for some reason the text is not coming up, and I don't know why. That's why I don't like using this. Let me do my eraser. See if I can get that. No, the eraser's not coming up. Okay, for some reason the pad is no longer working. Well, so much for typing in. I'll just read it to you. I said before, inertia was related to the mass of an object. On page 125, it reads, mass is a measure of the inertia of the body. That's exactly the reverse of what I was saying. Both of them are true. Mass is a measure of the inertia of a body. The larger the mass, the more its inertia, the more it tends to maintain its motion. Okay? The lesser the mass, the easier it is for it to change its motion. Okay? Think of, and the picture in the book is a good illustration of this. Think of the transfer truck. Do you see that? And then the little car. You see the picture? Yes or no? Still don't see it. What are you seeing? Huh? What's that? It's what? Which way? This way? The other way? Is it down? Up? There you go. You got it? Okay. Now, transfer truck, car. Which you reckon has the more mass? The truck by a big shot, right? Okay. Therefore, the car can make a sudden swerve, and because it has low inertia, low mass, it will move fairly quickly. That transfer truck, though, it can't make a sudden swerve, and that's why they'll jackknife on you. That's why you pull out in front of them, they cannot possibly stop in as quick a time as a car can because they have so much more force. Okay? The larger body in mass has a greater resistance to change in motion than does the smaller one. All right. So that's so much for Newton's first law of motion, the law of inertia. Let's now deal with the second law of motion. You know, I found out why. No, still not working. I can't get I can't get the text box to work. Can y'all see the text box on the thing that I'm clicking on? Or do you just see a whiteboard? You just see the whiteboard. You don't see the thing that says select, text, draw, stamp, spotlight. You don't see that. Okay. Well, I promise you, I'm clicking on the text, and that's what I did before. And all it'll do is draw. So I can't draw. So let me move on to 5.2. I'll just read them for you. And if you need me to repeat it, I will. Okay. 5.2 is going to be talking about forces. We've already mentioned forces. We were saying net force. We talked about friction force and pushing force and other like this, and the law of acceleration. This is the second law of motion, Newton's second law. He has three. This is the second one, called the law of acceleration. Now, do any of you remember what acceleration is? We talked about it last time. And well, Molly's not here any longer, so I was going to say this for her. But for anyone who picks up the video and listens to it later, let me describe this for you. Okay. Remember, you start at one position, you move to another position. Okay. You've had a change of displacement or a change of distance, right? Distance is a scalar quantity that's only measured in inches, feet, miles, whatever. Okay. A displacement, however, is with a direction. That's a vector quantity. Has the same distance measure, but it also has a direction. If you take the time rate of change of distance, that's what gives you speed. So the change of change of distance over change of time, that's say miles is your change of distance, hours is the change of time, your speed is in miles per hour. Your change of distance was in meters, meters per second. Okay, whatever. Those are velocity or speed quantities. Velocity being the vector quantity that has a direction with it, speed being the scalar quantity that does not have a direction associated with it. But if you change your velocity, that's what it means to accelerate. So acceleration is change of velocity per change of time. Remember, velocity was meters per second. If you change your velocity, it'll be meters per second per second. Now, I will write down that unit for you if I can. That would be meters per second. Y'all laughed at my drawing last time, didn't you? You're laughing again, I can tell. Per second squared. Meters per second squared, that would be a typical unit for acceleration. Change of velocity, meters per second per unit time, which would be another second. So meters per second, that would be meters per second squared. That's an acceleration. Okay. Now, the second law, sometimes it's called the law of acceleration. I can't write all this out. It won't let me do the text. I don't know why. All it's doing is letting me write by hand. Nope, not doing it. Okay. I don't know why. Let me see what happens if I do this. Okay, now I can't get it back. Ah, nope. Where did it go? Let's see if it'll let me do text this time. Nope. Something I'm not going to mess with anymore. Here's Newton's second law. The total force acting on a body is equal to the mass of the body times its acceleration. This is the most common form of Newton's second law. F, pretty pathetic, is equal to awful mass. Now this M, okay, this M up here is the unit for meter. Okay, you'd always have a number in front of it. 7 meters per second squared, 0.3 meters per second squared, -4 meters per second squared. This is a parameter. Force is a name something, M stands for mass, times acceleration. Oh, this A is going to be hard to, okay. That's Newton's second law. The net force acting on a body is equal to its mass times acceleration. Now let's go back and think. The first law said if there is no force acting on the body, that means there's no acceleration of the body. If the net force is zero, the acceleration is zero. What does that mean? It's going at a straight line motion, constant velocity, not changing speed, not changing direction. Acceleration is zero. But if there is a net force acting on the body, that means you are changing velocity. You've got to change velocity. That may be a change of direction. It may be a change of speed. But whatever is changing its velocity, that means it's accelerating. Okay? Now that acceleration may be negative. It may be positive. It may be in a direction, but it's changing its velocity. That's the acceleration. So that's what Newton's second law is. First law, if there's no net force, no unbalanced force, the velocity is constant. Okay? Meaning straight line motion, same speed, or being at rest, which is zero speed. Okay? But if there is a net force acting on it, that says it changes its velocity, meaning it accelerates. So there's the second law of motion. Okay? Now, if the mass is kept constant, if this mass is a constant quantity, that means the force is proportional to the acceleration. If you add more force, you're going to accelerate faster. If you're accelerating faster, that means you got to do more force. If you add less force, it'll accelerate less. Okay? those are proportional to each other. If the force is in the opposite direction of your motion, that means you're going to have a negative acceleration. The object's going to slow down. It was going this way fast, now it's going to slow down because its velocity is changing. Okay? Now, if you keep the force constant, the force is a constant, now the mass is proportional to the inverse of the acceleration. In other words, and this is the way they write it in the book, and this is going to be pretty pathetic, the mass is equal to, or it's actually proportional to, so this is supposed to be a wavy line, proportional to 1 over the acceleration. This is an ugly A, okay? That's supposed to be an A, folks, okay? 1 over the acceleration is proportional to that. That means if the acceleration is increasing at the same force, that means your mass is less. Or if the mass is greater, the acceleration is going to be less with the same force acting on it. Let's go back to the ping pong ball and the bowling ball, okay? You can hit a ping pong ball with a little, you can hit it with your hand, can't you? You can swat at a ping pong ball and send it winding, changes acceleration big time, okay? Okay, do that to a bowling ball, you're probably going to break your hand, or at least you're going to hurt your hand, bruise it, because the acceleration is inversely proportional to the mass. The larger the mass, the smaller the acceleration with the same force, okay? And that goes a variety of ways. Now, remember we have two basic set of units. One of these is SI, okay? Now, quite often we'll call SI the metric units. They're not quite the same. This is supposed to be an S, and that's supposed to be an I. Okay, that stands for System International. The French always put the modifier, quite often put the modifier after the noun. We usually say international system, okay? So this is the SI system. The unit for force in the SI system, mass, the unit for mass in the SI system. Now these are parameters down here. Here are the units. The unit would be for mass in SI is kilogram. That's 1,000 grams. Kilo means 1,000 grams. Acceleration, we just had it, it's right up here. It's mass, not mass, meters per second squared. These are the units, okay? This is the unit for force. Now, to keep from writing kilogram meter per second squared, every time you're talking about a force, they gave it a very special name, named after good old Sir Isaac Newton. So that's called a Newton. That's supposed to be a regular N. It looks pretty ugly, doesn't it? Don't answer that question. Okay, the force unit in the SI system is a Newton, a kilogram meter per second squared. These are units up here, okay? Units have numbers in front of them, 10 newtons, -3 newtons, whatever. That would be 10 kilogram meter per second squared or -3 kilogram meter per second squared. These are parameters. They just stand for the terms that you're representing. That means force is equal to mass times acceleration. Units, they have numbers in front of them. Parameters do not. So meters per second squared, if it has a number in front of it, M stands for meters. If it's just a formula, M stands for mass. Sorry, they use the same letters for both situations. Now, here's the problem in the U.S. customary system. They just call it the U.S. system. My S's look like 5s. The U.S. system. The unit for mass we never use. It is a slug. We never use it except in this book. This book uses it about half the time. No one else in the world uses a slug. That is the mass unit in the U.S. customary system. The distance unit in U.S. customary is feet. Okay? And then the time unit is still seconds. And because that's acceleration, that would be seconds squared. Okay, so, and what is this unit? The unit for force? This is a pound. Okay, that's supposed to be LB for pound. The U.S. customary unit for force is pound. A pound is a slug foot per second squared in mass times acceleration. No one uses slugs. So usually when we talk about forces, we talk about pounds in the U.S. customary system. We talk about newtons in the SI system. When we talk about mass, we use kilograms in the SI unit. We don't use anything. We don't talk about mass in U.S. customary. If you did, you'd have to use the term slug. Okay? The book uses it. No one else does. A pound is a slug foot per second squared. Really weird. Okay. I'm going to see if I can clear the whole board here. There, it did clear. Now let's see if we can do example 1. Actually, maybe I shouldn't have cleared it. I'm just going to do example 1 on a piece of paper. Okay. Let me see if I can find a piece of paper with enough room to write on it. Okay, this will probably do. I'm going to use ink. I usually use pencil, but the ink shows up better on the slide, I hope. Okay. So here's example 1. What force? So we're looking for force. That's the unknown here. So I usually put the unknown as a question mark. F, that's your unknown. Okay. What force is necessary to produce an acceleration of 6.00 meters per second squared? Now, just to give you an idea, that's an enormous acceleration. What that means is increasing its velocity 6 meters a second every second. Now, what is a meter? A meter is approximately a little bit more than a yard. Okay, so 6 meters would be just about 7 yards, not quite 7 yards. So 7 yards per second would be a speed that's going pretty fast, but it's increasing by 7 yards per second every second. So the first second, it would be, let's go back to meters, 6 meters per second squared. And then the next one, it would be 12 meters per second squared. And then the next second, it would be going to 18 meters per second squared. Now it's doing that gradually, but that is increasing with an incredibly large acceleration. But this is a problem. It doesn't have to make sense. Okay. On a mass, and the mass is 5.00 kilograms. Okay. Well, what was our formula for force? Anyone remember? Wish I'd have left it on the screen. What was force? Mass times acceleration. There's it written in my handwriting rather than the other. That's what force is, mass times acceleration. So all we do is plug in. The mass was 5.00 kilograms times the acceleration, 6.00 meters per second squared. That's the acceleration, and that gives us 30.0. You could write it as kilogram meter per second squared, or you could write it as 30.0 newtons, because a kilogram meter per second squared is a newton. Now, let's talk just a little bit about what those zeros are in there for. Does anyone know? Why didn't they just say 6 meters per second squared, 5 kilograms? Why did they put those zeros in there? Anyone have an idea? They're indicating precision of your measurements. This is an incredibly precise measurement. That's 6.00 meters per second squared. That means it's not 5.9, it's not 6.1, it's 6.00 to the nearest hundredth of a meter per second squared. That's your acceleration. It could be anywhere between 5.95 up to 6.05. Somewhere in between those, that would be precisely 6.00. No, I didn't say that right. Between 5.995 and 6.005. So it's a very, very precise measurement. Same thing for the mass. 3 significant digits means it's between 4.995 kilograms and 5.005 kilograms. Very precise measurement. So to get our precision, we see 3 significant digits here, 3 significant digits there. When we multiply and get 30, we can only get 3 significant digits there. That's why I didn't put 30.00. That would have been 4 significant digits. You can't get more significance out of a problem than you put into it. You put 3 and 3 in, you get 3 out. So that's why I put it 30.0 newtons, or 30.0 kilogram meter per second squared. Does that make sense? Yay or nay? Okay, good deal. So that's why the book has their answer 30.0 newtons. Okay, example 2 over on the next page says again, what force? So again, we're looking for force. Okay, is necessary to produce an acceleration. So this time we give acceleration of 2.00 feet per second squared. That's not nearly as fast of an acceleration as 6 meters per second squared. Still a pretty fast acceleration though. On a mass of, the mass then being 3.00 slugs. You can't even abbreviate slugs. They don't have an abbreviation for it. You have to spell it out. So there's our setup for this problem. We're looking for the force. You're given an acceleration of 2.00 meters per second, feet per second squared, and a mass of 3.00 slugs. I have no idea how much mass that is. Okay, I'd never use slugs. Okay, well, what is the force? The force is mass times acceleration. So this would be 3.00 slugs times acceleration 2.00 feet per second squared, and that would give us a force of 6.00 pounds. I'm not going to write it as slug feet per second squared. I could, but we just call it pounds. 2 times 3 is 6. Keep the 3 significant digits, 6.00 pounds. Does that make sense? Yay or nay? Okay, good deal. All right, that was example 2. Example 3. Now, if you didn't remember this from last time, I sure hope you have a piece of paper and pencil and you're working these problems right with me. So that's why I'm calling them out and saying them. This time it's asking for the acceleration. This is the unknown here. Okay? Now, let me back up for a moment and talk a little bit about formulas. Our formula, basic formula here for a Newton's second law is force equal mass times acceleration. Right? Remember that from writing on the screen? Force equal mass times acceleration. Can you see it? Yay or nay? Can you see this one? Force equal mass times acceleration. Okay. Now, our first 2 problems, that's what we did. We're looking for force. We just multiply mass times acceleration. In this problem, we're going to be looking for acceleration. So what we do with our formula is isolate the acceleration. Well, how do you do that? You get rid of the mass. And since the mass is multiplied, you get rid of it by dividing, but you divide it by both sides. So that's what I've done. I've taken the force equal mass times acceleration, divide both sides by mass, and on the left-hand side, or right-hand side, the masses go out, and that leaves me acceleration is equal force divided by mass. I'll switch sides on the thing. That's how you calculate what acceleration is. Does that make sense? Okay. Similarly, if we were looking for mass, it would be mass is equal to force divided by acceleration, right? You just divide both sides by acceleration then, and then your accelerations go out here and you have mass equal force divided by acceleration. Now, when I was in the Navy, I went to a few Navy schools and I found out they had this. Navy schools aren't the best in the world of anything, I don't think, but they were pretty good. But in everything like this, they recommended that people use what they call the triangle or the circle method. Okay, I'm going to draw them for you. Okay, and then I'll hold them up and tell you what I've done. Okay, now when you have, here's the triangle. You have one quantity in the peak up here, the others down here. The horizontal line is what you call a dividing line. That means division. The vertical line, I put the X, means multiplication. You can do it with a circle or a triangle. It doesn't matter which one you use, but a dividing line and a multiplication line. If you know a formula and you know force equal mass times acceleration, since it's mass times acceleration, put those on the bottom. Mass times acceleration, mass times acceleration. That means force is going to be on top. Okay? So this is how you'd set up your triangle. Always set it up that way. If you're doing Newton's second law, this is its triangle or its circle. Okay? So if you're looking for acceleration, cover acceleration, force divided by mass. That's exactly what we got here. It also works here. So if you don't want to remember how to divide out things, just remember your triangle or your circle. Okay? If you're looking for mass, that's force divided by acceleration. If you're looking for force, that's mass times acceleration. You get all three of them for the price of one. Okay? So this time we're looking for acceleration. This is example 3 on page 127. Produced by a force of 500 newtons. Now, this is how they wrote it in the book. They put 500, but on that second zero, they put a bar over it. That bar means that zero is significant. That means everything between the 5 and that is significant. So you have, again, 3 significant digits here. If you didn't put the bar over it, you assume the 5 is your only significant digit. If the bar had been over the first zero, that would only be 2 significant digits. Okay, so that's what the bar means. Significant, that the last zero is significant, it means all three of them are. Now, when they list the mass is equal to 20.0 kilograms. Now, they didn't need to put a bar over, where is it, over this zero, because anytime you have a decimal and you put a zero after it, that means you mean that to be significant. So you don't need the bar there. It's just when you don't have a decimal point and you have a whole number and with zeros in it, of course, if a zero is in between any other 2 digits, it's significant. Or if it's at the end of a number, it's only significant if it's got a bar over it. That's without a decimal. This one, since it follows a decimal, everything following the decimal will be significant. Okay? So there's your problem. What is the acceleration? If you're given a force and a mass, well, your formula that we were just doing, acceleration is equal to force divided by mass from our triangle or a circle or from our what they call literal equations when you solve your equations with letters. So that would be 500. Now, in this case, I'm not going to write down Newton. I'm going to write it down in its fundamental units. What was a Newton? It's a kilogram meter per second squared. That's what a Newton is. Divided by 20.0 kilograms. Okay. Now here's why I didn't use Newton. I put the fundamental units, kilogram meter per second squared. That's why it's important to remember those units. Okay. Divided by this. Now you see the kilograms cancel out. So you can just go on and cancel those out. Cancel out the kilograms. And then divide 500 by 20. Well, I'm going to do it in a fairly easy way. That last zero and 20 and will cancel out the last zero and the 500. You're basically dividing both by 10. And you got then 2 into 50 will be 25. 0.0, you need two significant digits, meters per second squared. Now you talk about an incredibly large acceleration that is, okay? 25.0 meters per second squared. There's no way you're going to maintain that acceleration for very long. If you did it for more than a tenth or two of a second, you're really at an incredibly fast acceleration. 25 meters per second. That means you're increasing its velocity 25 meters. That's more than a quarter of a football field in a second. Okay, increasing its speed 25 meters per second every second. That means after 1 second, you're going 25 meters per second. After 2 seconds, you're going 50 meters per second. And in 3 seconds, you're going 75 meters per second. If you can accelerate like that, Nick Saban wants to sign you up, okay, right now on the spot. And sure enough, that is the answer they had in the book. All right. Now, the three of you were here last time, plus another one was here last time too, I believe, maybe two. See, we had 1, 2, 3, 4, 5 here last time. We had 4 here today, dropped down to 3. And most of you responded, and that was perfectly fine. But none of you have books, right? Yeah, this is so bad. It's coming in the mail. Okay. Well, what you'll get when you get your book, you have what? A virtual book. Ebook. Okay. If you can see these problems when your books get there, on page 127, there are 8 problems at the bottom of the page. Do you sort of see them there? Okay. I would say do the odd ones. Here's why I say do the odd ones. The odd ones are in the back of the book. Now, do you have to do them all? No, not necessarily. I would do at least 1 or 2 of those 1 through 7. Okay. I do at least 1 in the SI units and at least 1 in US customary unit. Then over on page 127, any of the odds 1 through 7. Okay. When you turn to 128, there's a whole page full of problems. Now, at the top of the page, you see a few more that were similar to that one. So I would do at least 1, maybe 2 of 9 through 15. I would say at least 1, probably 2 of 9 through 15. You choose. Do at least 1 in US customary, and there's only 1 of them that is, and 1 of the other 3 in SI units. And then for the rest of them you have, that would be 17 through 33, takes up almost the entire page. Can you see that? Okay. Do any of those odds. Do some of every type that you see there. So until you feel confident, yes, I've got this down. Now, why do I say do the odds? Because the odds have the answers in the back. If you can't get the answer that's in the back of the book, bring that question to class and we will work it out in class. Okay? But usually by the time you see the answer and you go back and check, usually you'll find out, hey, okay, I figured out how they got it. But if you can't do that, don't get frustrated, don't waste a lot of time. Bring those that you can't do to class and we'll work them in class. Okay? All right. We're ready for 5.3 then. Okay? 5.3 is talking about 2 characteristics. One is the concept of gravity, and the next is the concept of weight. Okay? Now let's see if maybe I can get my text to work again. No, I can't. Do not know why the text key is not working anymore. Okay? So I'm going to have to write this out. Well, the first I'm just going to read to you. What do we mean by weight? The weight of an object is not, I want to say this carefully. Don't want to say it has nothing to do with the mass. It does, okay? But it's not the mass of the object. The weight of the object is the amount of the gravitational pull exerted on the object by the earth or any other object that the body happens to be on. We're going to be on the earth just about our entire lives. I will be on the earth my entire life, okay? I'm not planning to go out into space, okay? I don't know if any of you are either, but you're going to be on the earth most of your life. So we're all going to be, and we are experiencing the same gravitational pull on us. The earth is pulling down on us with an acceleration, okay? That's called the acceleration due to gravity. The result of your mass, my mass is bigger than your mass, I bet, times that acceleration due to gravity, which is the same for all of us, that gives us our weight. And that's why I weigh more than you do, my guess. Okay? Um, so what it is, the velocity, okay. So that's what weight is, the amount of gravitational pull exerted on an object by the Earth. Now, if that force is not balanced by other forces, an acceleration is produced. Now, they give the illustration in the book, and this makes sense. If you're there holding a brick, can you see the hand holding the brick there? Okay. If you're holding the brick, your hand is exerting a pressure, a force on the brick, keeping it from falling, right? And if you were holding that brick, you would know after a while, yes, I'm exerting force and I'm getting tired of doing it, okay? You're holding it up. If you were to release the brick, though, it starts to fall, right? And it falls at a certain acceleration. That's the acceleration due to gravity. And I'll tell you now, it's 9.80 meters per second squared. Or, in US customary units, it's 32 feet per second squared. It's increasing its velocity at 9.8 meters a second every second. It's increasing its speed at 32 feet per second every second. That's the acceleration due to gravity. Okay? Um, when you're holding it, you're exerting a force up. The brick's weight is down. That's why your hand gets tired. When you do release it, that's when the brick falls, and now all it has is a force due to gravity pulling it down. Okay? Now, I'm going to have to do this again. If you remember, Newton's second law was F. You tell me, what was Newton's second law? F equal. Okay, perfect. Now, what this force is the net force acting on the body that has that mass moving with that acceleration. If it's accelerating, there's got to be a net force making that accelerate. Okay, if there's a net force acting on the body, that means it's accelerating because of that body with that mass. Now, the weight formula looks very similar to this, okay, except this is now F, it's an ugly F, and they use a sub G, okay? That means the force due to gravity. The other word for force due to gravity is weight. So when you see F sub G, that means weight. When you read weight, that means F sub G, the force due to gravity. And that's the mass of the object times the acceleration due to the gravity. And on the surface of the earth, that's always a constant. So that acceleration is now called G. Okay? Now, they listed in the book the F sub W is, I'm sorry, other books say F sub W. I don't know if my eraser is not going to work. I don't think. Nope. Yeah, except this is supposed to be a W here, not a G. F sub W, not F sub G. But I can't get the eraser to work. That's F sub W. I misread it. Other books call F sub G. That's the formula for weight. This is the formula for a net force acting on a body. If the body is accelerating, that means there's a net force acting on it. But the weight of an object is F sub W, and that's the mass of the object times the acceleration due to gravity. For whatever planet or body you happen to be on, That's its acceleration. And for us on the surface of the Earth, that is, this G is in the US, in the SI unit, G is 9.80. That's what I started to write, and it made, okay, 9.80, three significant digits. Now I slashed my zeros, so that's why I put a slash through it. And that would be meters. The SI unit for length is meter per second squared. Getting a little bit better with my slash bar there, per second squared. Now that G in the US customary is 32. This is ugly writing. 2. That's really ugly. And that would be feet per second squared. Getting a little better at this, but it's still pretty ugly. Okay. Those are the constants of gravity on the surface of the Earth. Whether you're at the bottom of the Dead Sea Valley or at the top of Mount um, Everest, the highest point, the acceleration due to gravity, wherever you are on the surface of the Earth, is right at 9.80 meters per second squared, or 32.2 feet per second squared. Now, what does that mean? Here's a way to look at it. A meter is a little more than 3 times a foot, because there's exactly 3 feet in a yard, and a meter's a little bit longer than a yard, so that's why it's a little bit more than 3 uh, uh, meters, feet per meter. Okay. So let's do a couple of problems. I think I'll go back to my piece of paper so I don't have to write on the board any longer. Okay, if I can find my pen, know what I did with it. Yes. Right. Okay, now say that again. Right. Right. Okay, you mean get out of this. Okay, I thought I tried that before, but let's go back to the PowerPoint. Okay. Now, why it moved, we were on the next slide down. Okay. Uh, we'll try this and see if it works. It's a good idea, and let's try it. So let's do example 1 in this section. What is 5.3, I believe it is. Yeah, gravity and weight. It says find the weight. So you're looking for F. Oh, goodness gracious. What I was just doing, I'm left-handed, so my arm was landed on my computer top. Okay. Your weight is F sub W is equal to mass times acceleration due to gravity, mg, not ma, mg. Okay. It says find the weight, F sub w, that's what we're looking for. Okay. When of an object that is a mass of 5.00 kilograms. They didn't actually say that. They just said find the weight of 5.00 kilograms. But you have to say, hey, wait, what does kilogram measure? It measures mass. I went down and wrote it down for you. I'm sorry I did that. So we plug that into the formula. F sub W, that's what we're looking for, is mass times acceleration due to gravity. The mass is 5.00 kilograms times acceleration due to gravity. The SI unit would be 9.80 meters per second squared. Pull out your handy dandy calculators. I believe this comes up to be 49.0 newtons. Okay. Pull out your calculator and see if it works. I'm doing it from my head. It's this one right here. F is equal to mg. Your mass is, you're looking for the weight, and they said of an object that has, they didn't even say it. They said a 5 kilogram object, 5.00 kilogram object. Well, that happens to be the mass. Kilograms measures mass. You put that in the formula, F sub W is equal to M times G. The mass is 5 kilograms. The G is 9.80 meters per second squared. And when you multiply those out, use your calculator. I think it comes out 49, doesn't it? 5 times 9.8. Yeah. And you have to put 3 significant digits, so it's 49.0 Newton. Just like it was for forces, weight is a force. It's a force due to gravity. And that's 49 newtons. Okay. Now, and that's what we got, 49.0 newtons. Now, let's go to the next one. And see if I can find another piece of paper. I used most of the white space on that one. And I got a little bit on this one. Let me try this one. Okay. Find the weight of, whoops. Y'all are letting me go through supper, aren't you? It's now 6:30. We ran out of time. We'll pick up next time with example 2. Okay? On page 129. Now let's see if we did enough examples there. I think you can probably do example on page 131, example 1, and hold on, and you can do the rest later. So example 1 on page 131, section 5.3. So we'll pick up and go from there. I have 2 marks on the page. Let me erase one of them. All right. Any questions on anything we've done so far? And Jalen, you may be right, because next time we pull it up, hopefully the screen will work, okay? Because I'm going to shut down everything. But it would have been interesting to see if it would have worked here. Let's just see if it did. Let's try the whiteboard now. Okay. Nope, still not working. I think I have to shut it all off and bring it back up. But anyway, that's it for now. Any questions before we go? Okay, appreciate your attendance. I hope the others find us somehow. I don't see why it's a mystery, because it's out there on Blackboard every time. Did y'all have any trouble finding the invite? Okay. All righty. Well, we'll see you on Thursday then, okay? I'm ending the meeting now. Take care. All right. Let's end the recording.